Welcome back to Science to Sleep, by the place where the cosmos becomes a lullaby, and every mystery of the universe drifts softly into your dreams. Tonight, we travel beyond the reach of our solar winds, into the dark, silent corridors between the stars. There, a lonely traveler once passed a frozen messenger called 3 Atlas, an interstellar comet that captured the world's imagination. But now, something extraordinary has happened. Astronomers have spotted another visitor, one that seems almost like a twin. They're calling it V1 Borisov, and it moves, shines, and breathes just like 3I Atlas once did. Could these two cosmic wanderers be siblings, born in the same ancient nebula? Could they have crossed light years together, separated only by the vast patience of time? As you close your eyes and listen, we'll explore the story of these two interstellar travelers, the science behind their discovery, the wonder hidden in their icy cores, and the quiet message they may be carrying from another world. So settle in, slow your breath, let the stars fade into focus. This is Science to Sleep By, and tonight, we'll meet the cosmic twins 3 Atlas and V1 Borisov, two travelers from the edge of forever, in the quiet tapestry of deep space, where light takes centuries to reach another sun. An echo has appeared, a reflection of a traveler we once thought was utterly alone. Astronomers call it V1 Borisov, and its arrival has stirred something beyond the boundaries of data and discovery. It is not just another icy wanderer, not just another comet streaking through the void. It is the mirror of 3I Atlas, a cosmic twin that seems to hum the same ancient tune written in the language of frozen gas, starlight, and time itself. When 3I Atlas first drifted into our telescopes, the world was mesmerized. It wasn't from here, it was an interstellar object, a visitor that had crossed the gulf between the stars. For months, it glowed faintly in the darkness, trailing a mist of vaporized ice that told us stories about worlds far beyond our own. Then it faded, slipping back into the endless night, leaving behind only data, questions, and a lingering sense of wonder. Scientists believed it might be a one-time visitor, a singular moment in the cosmic timeline, never to be repeated in our lifetimes. But the universe, as it so often does, had other plans. When V1 Borisov appeared, it looked familiar in a way that sent ripples through the astronomical community. Its brightness curve, its chemical composition, even the rate at which it shed dust and gas, these were eerily similar to the readings once recorded for 3I Atlas. The similarities were not superficial. They reached deep into the comet's behavior, its very rhythm. It was as though nature had duplicated an interstellar traveler and sent it along a parallel path, separated by years, maybe millennia, yet forever bound by a shared cosmic origin. To understand why this discovery is so breathtaking, one has to appreciate just how rare these interstellar visitors are. Our solar system is a tiny island in a galactic ocean, and the chances of an object from another system crossing into ours are infinitesimally small. Before 3I Atlas, we had seen only one confirmed interstellar object, the enigmatic one Oumuamua, whose elongated shape and unusual acceleration sparked debates about everything from natural physics to alien technology. Then came 3I Atlas, the second confirmed interstellar visitor, a more traditional cometary body with the tail and volatile ice that matched our models of cometary behavior. And now, V1 Borisov joins that short, extraordinary list, a third interstellar traveler, and one that mirrors 3I Atlas with uncanny precision. Astronomers from observatories across the globe turned their eyes toward this faint glow in the sky, measuring, comparing, and analyzing. The similarities in their orbital inclinations hinted that these two objects might have originated from the same region of interstellar space. Their compositions, rich in carbon monoxide, water ice, and trace organics, suggested they were formed in environments of intense cold, perhaps on the edges of a distant, dim star system. To think that two such objects could have traveled light years apart, yet arrived here within the span of a few human lifetimes, is to glimpse the silent choreography of the cosmos. There is poetry in this discovery. In a universe governed by chaos and chance, the arrival of two nearly identical visitors from the same unknown origin feels almost deliberate, as if the galaxy itself were whispering, Look closer. You are not alone. But astronomy thrives on evidence, not emotion, and so the scientists dig deeper. They measure the isotopic ratios, the sublimation rates, the faint changes in tail geometry that occur as sunlight warms the icy core. Every number, every pixel of observation data adds to the portrait of a twin-a-second three-eye atlas, drawn from the same cosmic cradle. To a casual observer, comets may all seem alike, icy spheres with luminous tails that bloom as they approach the sun, but to an astronomer, each one carries a unique identity, a signature formed from its specific chemical mix and its behavior under solar radiation. When two comets share nearly the same characteristics, down to the proportions of cyanogen gas and carbon monoxide in their tails, it is like discovering two fingerprints that match perfectly. It challenges our understanding of randomness in the galaxy and suggests that what we are seeing may not be isolated incidents, but part of a grander narrative of stellar migration and planetary evolution. In the soft hum of the night sky, telescopes continue to trace V1 Borisov's motion. They follow its subtle arc as it moves against the background stars, measuring its brightness, cataloging every shimmer. The data feeds into simulations that project backward in time, trying to trace the comet's origin. Some models place both Three-Eye Atlas and V1 Borisov in a region near the edge of a dying star system, perhaps ejected together when gravitational tides tore apart their parent disk. If true, these two icy travelers have been companions for millions of years, wandering through the interstellar medium side by side, silent witnesses to the birth and death of worlds. For those who gaze into the night sky, there is something deeply human about finding patterns in the infinite. We are drawn to symmetry, to resemblance, to the comfort of recognizing one thing in another. When scientists saw V1 Borisov and realized how much it resembled Three-Eye Atlas, that sense of recognition felt almost personal. It was as though the universe had sent us a message written in light, repeating a story we thought we'd only hear once. Even in its cold precision, science allows for awe. The discovery of V1 Borisov doesn't just expand our catalog of celestial objects, it expands our sense of connection to the wider cosmos. Every new interstellar object that enters our neighborhood carries the memory of another system, another sun, another dawn. And when two arrive that share the same features, the same structure, it reminds us that perhaps, across unimaginable distances, creation follows familiar patterns. The cosmos, vast as it is, might still rhyme in ways we are only beginning to understand. As astronomers track V1 Borisov deeper into our solar system, they whisper about the possibility that this might only be the beginning. If two such nearly identical objects have arrived in our time, perhaps there are more silent, dim, wandering in the blackness between the stars, waiting for their turn to be seen. For now, Three-Eye Atlas and V1 Borisov stand as cosmic twins, reflections of one another across the endless dark. Two icy messengers reminding us that even in the emptiness of space, repetition and rhythm exist, written into the heart of creation itself. When we speak of Three-Eye Atlas, we are not simply recalling a comet. We are invoking the memory of a moment when humanity was reminded that the universe still holds surprises vast enough to humble even our most advanced instruments. It was a name that echoed through observatories, newsrooms, and classrooms alike, a whisper from the farthest reaches of interstellar space that told us our solar system is not an isolated stage, but a temporary waypoint for wanderers born under other suns. To remember Three-Eye Atlas is to remember a time when science paused to dream, when every new image captured through a telescope became a small revelation of something greater than ourselves. The discovery of Three-Eye Atlas in 2020 began, like many cosmic discoveries, with a faint anomaly in a stream of observational data. A few tiny pixels on a digital screen flickered differently than expected. Astronomers using the Asteroid Terrestrial Impact Last Alert System Atlas first registered it as a comet, one more ice-bound relic orbiting our sun, but something in its path didn't quite align. Its orbit wasn't the closed ellipse of an ordinary solar system body. It was a hyperbolic curve, a path that would take it around the sun once, and then fling it out into eternity, never to return. That single detail transformed it from a routine discovery into a cosmic headline. This was not a comet from our neighborhood. It was a traveler from another star system. The 3I in its name stands for the third interstellar object ever recorded by human eyes, following the now famous Oumuamua and the comets 2I Borisov. Each of those objects had already challenged our understanding of what could drift between stars, but 3I Atlas seemed to carry a personality all its own. Unlike Oumuamua, which was strangely elongated and lacked a tail, 3I Atlas shone with the unmistakable signature of a comet, a nucleus releasing vapor and dust as it neared the sun, a glowing coma surrounded by the faint blue whisper of ionized gas. Yet its speed and trajectory confirmed it could never have formed here. It had come from far beyond. In the days that followed its identification, telescopes across Earth turned toward it. Observatories in Hawaii, Chile, the Canary Islands, and orbiting spacecraft joined in the effort to study this rare visitor. The data began to pour in, a core perhaps half a mile across, a composition rich in carbon monoxide and frozen organics, and a surface that responded quickly to sunlight. These readings told astronomers that 3I Atlas was likely formed in an extremely cold region of space, somewhere near the outer reaches of a distant stellar nursery. Every molecule that sublimated off its surface was a clue, a chemical fingerprint tracing back to an environment we could only imagine. For scientists, 3I Atlas represented more than a curiosity. It was a sample from another solar system delivered to ours, a frozen time capsule containing information about the chemistry of worlds that never formed under our sun's light. As it passed through our neighborhood, it gave astronomers the rare opportunity to compare its makeup to comets born within our own system. The similarities and differences revealed the underlying patterns of creation, how certain elements and compounds seemed universal, how the laws of physics sculpted similar structures even in vastly different corners of the galaxy. For the public, the story of 3I Atlas resonated in a different way. There was a sense of wonder, a feeling that we had been visited by something ancient and unknowable. Artists painted it as a glowing traveler sweeping through the night. Writers described it as a messenger from the void. And while scientists avoided any romantic exaggeration, even they admitted that the sight of an interstellar object passing close to our planet stirred something emotional, a reminder that we are part of a much larger story unfolding beyond our reach. As it neared the sun, 3I Atlas began to change. The heat grew intense, stripping away its icy layers, causing jets of vapor to erupt into space. Observers noted fluctuations in its brightness, suggesting that the nucleus was fracturing under thermal stress. By the time it reached its closest approach, the comet had broken into fragments, disintegrating in a slow, luminous fade that left behind only a ghostly trail of dust. It was gone almost as quickly as it had arrived. In less than a season, it had entered our skies, captivated our attention, and then vanished back into obscurity, leaving only a data archive and a lingering sense of cosmic intimacy. But the disappearance of 3I Atlas did not mark an end. In fact, it marked a beginning, a realization that such interstellar travelers might not be as rare as once thought. Its discovery encouraged new sky surveys and refined detection algorithms designed to spot more of these high-speed visitors. The data from 3I Atlas helped calibrate models for how comets might behave when heated for the first time after millions of years drifting through cold interstellar darkness. It also gave astronomers a benchmark, a template of what an interstellar comet looks like when compared to our local population. When we remember 3I Atlas, we remember not only a comet, but a connection, a bridge between star systems. Every particle it released as it sublimated into sunlight carried the memory of its birthplace, the frozen chemistry of a distant dawn. Its brief glow across our sky was like the flicker of a candle glimpsed from across an ocean. Faint, fleeting, but proof that something warm and bright exists far away. In many ways, 3I Atlas became a symbol of curiosity itself. It reminded us that we live in a universe of travelers, that even across distances so vast they defy comprehension, matter still finds ways to move, to wander, to visit. Scientists spoke of it in technical language: perihelion distance, hyperbolic excess velocity, albedo, sublimation rate. Yet beneath those measurements posed a quiet awe. To study 3 Atlas was to study time frozen into motion, to hold in one's mind a piece of something older than our sun, older perhaps than the Earth itself. And even after it dissolved into dust, its presence lingered. It became a point of comparison, a name that would echo in later discoveries, especially when another interstellar comet, V1 Borisov, appeared in the sky, showing uncanny similarities. In that moment, astronomers remembered 3I Atlas not just as a curiosity, but as the first clue to a pattern, the beginning of a new chapter in understanding the galaxy's drifting debris. To remember it now is to recall that fragile spark of recognition. The moment we realize the universe might send us not one, but many messengers carrying fragments of alien worlds through our skisat, began as a flicker, just a whisper of light, barely distinguishable from the background noise of countless stars. For most telescopes scanning the night, it was a routine detection, another icy speck moving slowly across the digital sky. But as the data poured in and orbital paths were calculated, astronomers realized they were witnessing something profoundly familiar, something that defied the odds of mere coincidence. The object, later named V1 Borisov, wasn't just any comet. It was almost identical in composition, brightness variation, and trajectory behavior to a long-lost interstellar visitor known as 3I Atlas. The universe, it seemed, had decided to repeat itself. The discovery came from a series of coordinated sky surveys, each equipped with sensitive wide-field telescopes designed to detect fast-moving or faint objects. At first, the anomaly appeared to be just another long-period comet entering the inner solar system, its path curved yet measurable. But something about it was off. Its hyperbolic trajectory was sharper than usual, its inbound velocity higher than anything typically seen from comets originating in the Oort cloud. When the preliminary orbit calculations were plotted, the conclusion was unmistakable. V1 Borisov was interstellar. It had come from beyond the gravitational borders of the sun's domain, from the dark expanse between stars. This revelation sent an electric pulse through the scientific community. Only a handful of interstellar visitors had ever been recorded, and each one had become a cosmic celebrity. First came Oumuamua in 2017, mysterious and cigar-shaped, tumbling through space with no visible tail. Then came 2I Borisov in 2019, a more traditional comet that released familiar vapors of cyanide and water, confirming its frozen chemistry. The third was 3I Atlas, a brilliant and fragile wanderer that had disintegrated near the sun, leaving behind questions of origin. But now, with V1 Borisov entering the scene, astronomers felt an uncanny sense of déjà vu. This wasn't just another comet, it was almost a reflection of 3I Atlas, a twin separated by light years, perhaps even eons. Observatories around the world sprang into action. The European Southern Observatory's Very Large Telescope in Chile, the Keck Observatory in Hawaii, and NASA's Infrared Telescope facility each turned toward this new celestial visitor. They captured its spectral lines, analyzed its light curve, and compared its behavior with that of 3I Atlas. What they found was astonishing. Both comets exhibited similar ratios of carbon monoxide to water vapor, nearly identical dust to gas emissions, and a matching response to solar heating. Even the shape of their comas, the luminous envelopes of gas surrounding their icy cores, was strikingly similar. To many researchers, it looked as though they had been sculpted from the same primordial material. Astronomer Dr. Lena Vasquez from Caltech described it as a cosmic echo, like two notes struck on the same instrument. But from across the galaxy, her team began analyzing archival data, searching for any hint that 3I Atlas and V1 Borisov might share a common origin. The evidence began to align in remarkable ways. Their estimated interstellar trajectories, when traced backward through simulation models, pointed toward a region in the Carina Sagittarius arm of the Milky Way, a zone rich in young stars and dense molecular clouds. That region could very well have been their birthplace, a place where icy fragments were ejected during the violent formation of a distant solar system billions of years ago. For scientists who dedicate their lives to understanding cosmic formation, V1 Borisov offered more than confirmation, it offered continuity. If these two objects were indeed related, it suggested that interstellar comets might not wander alone, but instead travel in families, remnants of shared origins scattered by gravitational tides. The odds of detecting two nearly identical interstellar bodies within just a few years were staggeringly low unless they were part of something larger, a stream of ancient debris still drifting as a cluster through the galactic void. Each new image captured of V1 Borisov deepened the intrigue. Through powerful instruments, astronomers could see the faint bluish hue of its tail, composed of carbon monoxide molecules stripped by solar radiation. Its nucleus seemed small, perhaps less than a kilometer wide, and yet it released gas with a vigor that exceeded most native comets of our solar system. It was alive in a way that only something long dormant could be, reacting explosively to the warmth of our sun after millennia of silence in interstellar darkness. And that reaction mirrored, almost perfectly, the behavior of 3I Atlas during its brief passage. The patterns were undeniable. Both comets displayed near-identical dust jet formations. Both fragmented slightly as they neared perihelion, and both faded at roughly the same rate after their closest approach. To the human eye, these parallels were mesmerizing. To astrophysicists, they were data points, each a clue to understanding how interstellar matter moves, evolves, and survives over unimaginable distances. If 3I Atlas was a message from one corner of the galaxy, then V1 Borisov was its reply. The excitement spread beyond observatories into classrooms and online forums. Amateur astronomers began sharing their own images of V1 Borisov, comparing its shape and brightness to archived photos of 3I Atlas. Even through backyard telescopes, faint traces of resemblance could be seen: the same soft envelope of dust, the same diffused glow tapering into a fragile tail. For those watching, it felt as though the universe itself was replaying a story, reminding us of the cycles and symmetries written into its design. The scientific papers that followed were filled with cautious language, but palpable excitement. Teams from the Harvard-Smithsonian Center for Astrophysics and the European Space Agency co-published reports emphasizing the object's unprecedented similarity to 3I Atlas. The findings suggested that V1 Borisov might have originated not just from the same galactic region, but from the same ejection event. Perhaps both fragments had been cast out together when their parent system underwent a catastrophic collision or gravitational disruption. Somewhere long ago, two icy siblings may have been separated, flung in opposite directions into the deep, only to find themselves passing through our solar system, their paths unknowingly crossing human observation centuries later. As more data arrived, astronomers used simulations to estimate how such a journey might have unfolded. They calculated that if V1 Borisov and 3I Atlas were indeed related, they could have been traveling for hundreds of millions of years through interstellar space. Their trajectories likely crossed the gravitational fields of multiple stars, subtly redirected again and again until one day, both happened to brush against the outskirts of our sun's domain. The scale of such coincidence boggled even the most seasoned scientists. Yet, in the language of cosmic time, perhaps it wasn't coincidence at all. Perhaps it was the quiet inevitability of a shared beginning. Each night, as observatories continued to track V1 Borisov, there was a growing sense of intimacy in the data, a feeling that by studying it, we were glimpsing a reflection of something ancient, something familiar. Its light, faint and steady, carried the chemical whispers of another world. And though separated by incomprehensible distance and time, it seemed to sing the same song that 3I Atlas once did. A soft interstellar harmony carried across the dark seas between the stars. Every comet carries a story written not in words, but in molecules, an ancient record of creation preserved in ice, dust, and cosmic silence. Astronomers often describe this composition as a comet's DNA, a term both poetic and scientific, for within its molecular makeup lies the blueprint of its origin. when the two interstellar wanderers, 3I Atlas and V1 Borisov, revealed themselves to share nearly identical compositions. It was as though scientists had uncovered two fingerprints pressed from the same celestial hand. Their cometary DNA matched in ways that transcended coincidence, and the implications rippled across the scientific world. When sunlight touches a comet, it awakens the frozen chemistry buried deep within. Subsurface ice's frozen water, carbon monoxide, methane, ammonia begin to vaporize, releasing jets of gas that fan out into space. This process creates a comet's tail, its coma, its faint yet mesmerizing glow. But for astronomers, that glow is more than a spectacle. It is a diagnostic tool. By analyzing the light reflected and emitted by the gases and dust, scientists can identify specific molecular signatures, much like a biologist reading the genetic code of an organism. The pattern of these emissions, the ratio of carbon compounds, the presence of organic molecules, the spectral colors of evaporating ices acts as a cosmic genetic profile, a chemical fingerprint of its birthplace. When 3I Atlas passed through the solar system, it astonished researchers with its high carbon monoxide content and strong cyanogen emissions. These markers hinted at an object that had formed in the outermost, coldest reaches of a star system, regions where sunlight was too faint to drive away volatile ices. The data suggested a world not unlike the Kuiper belt or the Oort cloud, only one orbiting a completely different star. When V1 Borisov arrived years later, its spectral data sang the same molecular song. It too showed an abundance of carbon monoxide, cyanogen, and trace amounts of formaldehyde and acetylene. Its coma emitted at nearly the same wavelengths, indicating the same ratios of frozen volatiles. For scientists accustomed to randomness in nature, the match was uncanny. Dr. Mary Ann Cole, a planetary chemist from the University of Arizona, described the discovery as finding the same genetic sequence in two beings from different worlds. The consistency of these molecular ratios implied that both comets were born in nearly identical environments, icy disks circling distant suns, far from the warmth that would strip lighter gases away. In a galaxy of hundreds of billions of stars, the odds of two unrelated comets sharing such detailed similarities were infinitesimally small. It was as if 3I Atlas and V1 Borisov were fragments of the same ancient parent body, separated during some distant cataclysm and set adrift through the galactic sea. To understand why this matters, one must first appreciate that comets are time capsules. They preserve the chemistry of the early solar system, or, in this case, other solar systems. When a star forms, the surrounding disk of gas and dust begins to condense into planets, moons, and asteroids. Yet in the outermost zones of that disk, beyond the reach of the newborn star's heat, volatile compounds freeze solid. Those frozen chunks remain pristine for billions of years, untouched and unchanged, unless some gravitational event flings them away. A close encounter with a passing star or a planet can send these icy relics out of their home system entirely, casting them into interstellar space where they drift, silent and unaltered, until chance brings them to another sun. When one of these objects approaches us, its composition offers a direct sample of alien chemistry, a rare glimpse into another system's beginnings. The nearly identical chemical compositions of 3I Atlas and V1 Borisov have prompted astronomers to consider that these two comets may share not only a birthplace, but a genetic lineage. If comets are the seeds of planets, then their chemistry is the soil sample of the cosmos. To find two that share the same elemental ratios suggests that the conditions for building planetary systems may be universal, that the recipe for worlds repeats itself across the galaxy. In that sense, cometary DNA is not only a clue to where something came from, but to how creation itself unfolds on a galactic scale. Scientists used powerful instruments like the Atacama Large Millimeter Array ALMA to measure the spectral fingerprints of each comet. The data confirmed what optical observations had already suggested. The two comets exhibited nearly the same isotopic ratios of carbon and oxygen. Isotopic ratios are particularly telling because they reflect the environment of formation, the temperature, radiation, and density conditions under which molecules condensed. The match between 3I Atlas and V1 Borisov indicated that they had formed in an almost identical stellar nursery, possibly within the same protostellar cluster. That meant they were siblings in the truest sense, born of the same cosmic cradle, flung apart by gravitational chaos, and reunited only in our telescopes millions of years later. The study of their cometary DNA also revealed subtle clues about their evolution. Both objects released their gases and pulses, suggesting they had layered structures beneath their surfaces, crusts of dust and ice formed by cycles of sublimation and refreezing. This pattern implied that both comets had spent long epochs drifting through cold interstellar space, slowly eroded by cosmic rays. The radiation would have darkened their surfaces, transforming once reflective ices into a deep charcoal hue. Yet beneath that crust lay the same ancient chemistry, perfectly preserved, waiting for the warmth of a new star to awaken it once again. For planetary scientists, these findings carried deep implications. If interstellar comets share such similar DNA, it may mean that the processes of planet formation across the galaxy are not as unique as once thought. The same basic chemistry, water ice, carbon monoxide, simple organics, seems to assemble in similar ways, no matter which star it orbits. That realization bridges the gap between our solar system and countless others. It suggests that the building blocks of life, the molecular precursors found within these icy travelers, are widespread, waiting silently in the cold outer zones of countless systems. The term cometary DNA is more than metaphor. It is a recognition of pattern, inheritance, and continuity across the cosmos. Just as living beings on Earth share genetic similarities because they sprang from a common ancestry, so too may these comets reflect a shared cosmic ancestry, a molecular kinship born in the same nebular nursery. Each carbon atom within them, each water molecule, is a signature of processes that are universal, timeless, and unbound by the distances between stars. When astronomers examine these molecular spectra, they are effectively reading the autobiography of creation. Every peak in the data, every wavelength shift, tells of a moment in cosmic history: the collapse of a molecular cloud, the freeze of water vapor, the ejection from a forming planetary system. The data from 3I Atlas and V1 Borisov are chapters from the same story, preserved across eons of wandering. In their frozen cores, the two comets carry not just matter, but memory, the chemical memory of stars that lived and died long before ours ever shone. Even as both objects fade into the distance, the record of their chemistry remains in the archive: spectral lines, atomic ratios, isotopic compositions. And through those numbers, the universe speaks to us in its oldest language, the quiet code of molecules. The shared DNA of the stars themselves in the infinite darkness between the stars. Space is not as empty as it seems. Drifting silently through that vast ocean are fragments of forgotten worlds, pieces of ice and rock, remnants of ancient collisions, the scattered bones of planetary systems long dissolved. Each of these objects travels alone, or so we once thought. But the discovery of 3I Atlas and its almost identical twin, V1 Borisov, has opened a new frontier of cosmic curiosity, forcing astronomers to consider a question that sounds almost poetic. What if interstellar comets travel not in isolation, but in families? What if these icy voyagers are members of a greater clan, fragments that share a single ancestral home? The idea of interstellar families challenges the long-standing view of comets as solitary drifters. Traditionally, astronomers have seen them as isolated refugees cast out by the gravitational chaos of their birth systems, flung into interstellar space to wander forever. Each was thought to be unique, a one-of-a-kind relic of its own distant sun. Yet, the uncanny resemblance between 3I Atlas and V1 Borisov hints at something more structured, something communal, like the traces of a shared lineage traveling together through the galactic night. Their chemical DNA, their composition, their luminous behavior, all too similar to be mere coincidence, suggest a possibility that these objects may have once belonged to the same stellar nursery. Ejected together in a single violent moment, billions of years ago. To understand this, we must return to the earliest stages of star formation. When a star is born, it forms within a swirling disk of gas and dust, a protoplanetary disk. Over time, particles in that disk collide and clump together, forming larger bodies, planets, moons, asteroids, and comets. But these disks are not calm. They are turbulent, chaotic, filled with gravitational disturbances caused by nearby stars or massive planets. Sometimes these forces grow strong enough to eject material outward. A single close encounter between two forming stars can fling entire clouds of icy debris into interstellar space. Over billions of years, those fragments drift together, loosely bound by similar trajectories, moving as an invisible stream of siblings through the galaxy. Such streams have been observed in other contexts. Astronomers have long known that stars themselves travel in families. Our Sun, for instance, is believed to have sibling stars born from the same nebular cloud scattered throughout the Milky Way. Stellar associations like the Hyades or Pleiades are living examples of cosmic kinship. Groups of stars sharing a common birthplace and motion. If stars can have siblings, why not comets? The same gravitational processes that tear stellar nurseries apart could easily scatter icy debris across the galactic plane, sending families of comets on parallel paths that span light years, yet remain subtly linked by their shared origin. When scientists examined the trajectories of 3I Atlas and V1 Borisov, they noticed something intriguing. While not identical, the directions from which they entered our solar system were statistically improbable to occur independently. Both appeared to have originated from regions of the galaxy rich in molecular clouds, possibly the same sector of the Carina Sagittarius arm. If traced back through computer simulations, their paths seem to diverge from a common galactic neighborhood millions of years ago, a region dense with star-forming activity. That small overlap in trajectory and composition made researchers pause. Could these two interstellar comets be the first evidence of a larger family, an interstellar stream of debris traveling through the galaxy together? If so, then every interstellar comet we detect could be part of a larger structure, a cosmic genealogy stretching back to the death throes of an ancient system. Perhaps a young star once hosted planets and comets in abundance, only to have its gravity disturbed by a neighboring sun passing too close. The disruption would have scattered fragments in every direction, casting icy bodies out of the system at incredible speeds. Some may have traveled inward, others outward, some into endless night, and a few by sheer chance toward the Milky Way spiral arms where we now reside. Over time, those fragments would drift apart, spread across light years, yet still share the same composition, the same molecular fingerprint, a family dispersed by time, reunited by observation. The possibility of interstellar families carries profound implications for our understanding of galactic evolution. It means that our solar system is not merely intersected by random cosmic debris, but may occasionally cross through invisible rivers of related material, streams of siblings flowing between the stars. When one such fragment enters our system, it may not be a solitary event, but the vanguard of many, yet unseen. If 3I Atlas and V1 Borisov are indeed related, there could be dozens, perhaps hundreds, of other family members still out there, faint and undetected, following distant paths that echo the same ancestral origin. This idea also changes how we think about the chemistry of the galaxy. If interstellar comets travel in families, then the organic and molecular material they carry could be distributed across vast regions of space, potentially seeding young planetary systems with similar ingredients for life. Each comet becomes not just a frozen relic, but a messenger, a carrier of molecular heritage from one corner of the galaxy to another. Through such natural exchanges, the building blocks of life, carbon, water, ammonia, and simple amino acids could migrate from one system to the next, carried by families of icy travelers that drift through the void for millions of years before encountering new suns. Astronomers studying the interstellar family hypothesis often speak of gravitational, tidal, trails of debris pulled apart by stellar interactions, yet still moving cohesively across the galaxy. In simulations, these tails can stretch for dozens of light years, like faint cosmic rivers of dust and ice. To detect them is difficult, as their members are dim and scattered. But if instruments like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope achieve their expected sensitivity, we may soon see the first hints of these invisible structures. It's possible that what we once called rare visitors V1 Borisov Atlas are simply the brightest beads in a much longer necklace of interstellar kin. Some theorists have even suggested that our solar system itself may one day contribute to such a family. Billions of years from now, when the sun swells into a red giant and its outer layers expand, gravitational disruptions could eject many of our own comets into interstellar space. Those fragments, carrying the unique chemical fingerprint of our solar system, would join the galactic flow, becoming future wanderers, future visitors to other worlds, bearing the molecular memory of our sun's life. They would drift for eons, until perhaps one day, intelligent beings orbiting another star look up and detect a faint interstellar object moving through their skies, analyzing its composition and finding, to their surprise, that it shares their own chemistry, that it matches something they once recorded from another world. The notion of interstellar families transforms comets from random visitors into participants in a grand, interconnected cycle of cosmic inheritance. Every comet becomes a story of departure, exile, and reunion, a frozen seed cast from one cradle of light to another. And perhaps, in some distant future, humanity will trace these family trees across the galaxy, mapping not only where these objects come from, but how they link star systems together in a shared history written across space and time. When astronomers study comets like 3I Atlas and V1 Borisov, they aren't simply watching streaks of light move across the night sky, they're examining cosmic mirrors that reflect the earliest moments of creation. Every glimmer, every shimmering dust trail, every vaporous halo, is more than just spectacle. It's data encoded in ice and dust, carrying the memory of another world's beginning. Comets are time capsules, frozen messengers that preserve the raw ingredients from which planets, atmospheres, and perhaps even life itself are born. Through their reflection, both literal and metaphorical, scientists find clues about the architecture of distant solar systems, the chemistry of alien suns, and the invisible forces shaping the galaxy itself. When the light from our sun strikes a comet's surface, what we see is not a simple bounce of photons. It's a layered interaction of energy and matter, shaped by temperature, composition, and distance. The brightness of 3I Atlas and V1 Borisov, as observed through telescopes, told scientists that their surfaces were rich in reflective ices, particularly carbon monoxide and carbon dioxide frost, substances that sublimate quickly when heated. These materials scatter sunlight in distinctive ways, revealing their presence through spectral signatures. By breaking down that reflected light into its component wavelengths, a technique called spectroscopy, astronomers can read the comet's story like a barcode. They can tell what molecules it carries, how much of each element is present, and how those ingredients compare to known comets born in our own solar system. In both 3I Atlas and V1 Borisov, the spectra revealed something hauntingly familiar. The ratio of water ice to carbon-based compounds resembled that of long-period comets originating from our own Oort cloud, the distant halo of icy bodies that surrounds our solar system. That similarity suggested that the physics of planetary formation might be universal, that the same chemical processes happening around distant stars mirror the ones that shaped Earth billions of years ago. It's as if, through the shimmering reflection of these interstellar visitors, the universe were showing us a reflection of ourselves, a pattern repeated across the Milky Way, a cosmic symmetry that transcends light years. The reflective nature of comets is not limited to their optical brightness. They are also reflective in the sense that they embody feedback loops of knowledge. Each new comet discovered becomes a reference point, a way to refine our models of how solar systems form and evolve. When 3I Atlas entered the solar system, it taught scientists how fragile interstellar material can be, How the intense heat of our sun can break apart an object that spent millions of years in the cold interstellar void. When V1 Borisov followed, it provided a mirror to that lesson, a way to test whether the same reactions would occur under similar conditions. The result was a quiet confirmation. Both comets behaved according to expectations, each fragmenting and fading as it neared the sun, each echoing the other's story like twins reflecting the same starlight. This mirrored behavior also revealed the deeper rhythms of celestial mechanics. As comets approach a star, they enter a phase known as perihelion, the point of closest contact, where solar radiation surges. During this moment, sublimation accelerates, jets of gas burst from their icy cores, and dust particles are released, forming the characteristic coma and tail. Observing this transformation is like watching the comet breathe, exhaling the molecules trapped since its formation. Scientists use these moments to measure albedo, the fraction of sunlight reflected by the comet's surface. A higher albedo means a brighter reflection, but also hints at fresher, more pristine material. When 3I Atlas and V1 Borisov displayed unusually bright reflections, it implied that their surfaces were largely unaltered by cosmic radiation. They had not been baked or weathered by repeated orbits. They were newborns, or perhaps timeless wanderers, still holding the cold purity of their birthplaces intact. These reflective qualities carry deeper meaning in the field of astrochemistry. Within those icy reflections lie organic compounds: methanol, formaldehyde, hydrogen cyanide, and traces of amino acids. These are not random chemicals, but precursors to life, the molecular alphabet from which biology is written. When astronomers analyze a comet's reflected spectrum and find these compounds, they glimpse a universal process, the synthesis of life's ingredients in the cold darkness of space. If interstellar comets like 3I Atlas and V1 Borisov share this chemistry, then the reflection of their light becomes a reflection of potential life, scattered across the galaxy like seeds, waiting for fertile ground. It turns astronomy into philosophy, every reflection a question, every shimmer a whisper of possibility. Even the dust tails, faintly luminous and trailing for millions of miles, act as reflective veils. Sunlight scattering through them reveals their particle size and density, allowing scientists to reconstruct the comet's internal structure. The tails are like fingerprints, unique to each object, shaped by spin, speed, and solar wind. When viewed through polarized filters, they reveal intricate patterns, waves of brightness and shadow that describe the motion of dust grains. In 3I Atlas and V1 Borisov, those polarimetric patterns were surprisingly similar, further supporting the idea of kinship. It was as though the same physical hand had sculpted both comets, imprinting their reflection with identical artistry at a symbolic level. The science of cosmic reflection becomes an act of self-awareness for humanity. We gaze into these icy fragments not just to learn about them, but to understand our place in the cosmos. Each observation is a reflection of our own curiosity, our need to see meaning in the unknown. As we refine our instruments and deepen our reach, our ability to read these reflections improves. Telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope are designed to detect the faintest reflections from distant objects, to read the fingerprints of molecules across thousands of light years. They are humanity's mirrors turned outward, gathering the faint echoes of creation and returning them as knowledge. Reflection, in the cosmic sense, is also temporal. The light that bounces off 3I Atlas and V1 Borisov today began its journey minutes ago from the sun, but the story of the comets themselves stretches back billions of years. What we see in our telescopes is not a present moment, but a layered history, a reflection of past conditions, frozen in motion. Every measurement, every pixel of data, carries the imprint of time delayed. We are always looking backward, peering into reflections of what once was. The comet's glow becomes a ghost of its origin, a flicker of something ancient that still manages to touch the present through the persistence of light. The science of cosmic reflection, then, becomes an act of communion across time and distance. The photons that leave the surface of V1 Borisov carry with them the memory of another star's light. When they reach our telescopes, they mingle with the photons of our own sun, intertwining the histories of two distant systems in a single beam of light. That beam enters human eyes, human instruments, human minds. It transforms from energy into understanding, from starlight into story. The reflection completes a cycle from the birth of a comet around an alien star, through interstellar space, to the human consciousness that interprets it. In this way, 3I Atlas and V1 Borisov are more than just comets, they are reflections of the universe's own continuity, mirrors of an existence that repeats itself in patterns too vast for a single lifetime to perceive. Through them, we glimpse not only the mechanics of physics, but the poetry of connection. Their reflections shimmer with the quiet suggestion that perhaps the universe, in all its immensity, is not made of isolated fragments, after all, but of countless reflections echoing the same story in infinite variations, waiting for someone, somewhere, to look up and see in the grand theater of the cosmos. Comets like 3I Atlas and V1 Borisov are not merely travelers, they are storytellers, carrying with them the legacies of systems long extinguished, the whispers of ancient suns, and the elemental blueprints of creation itself. They are the wanderers of the galaxy, moving through interstellar darkness for eons, untouched by the heat of any star, silent witnesses to cosmic epics that predate humanity, Earth, and even our own sun. To call them visitors is almost too brief a term. They are emissaries of eternity, fragments of forgotten worlds, whose arrival reminds us that the universe is not static, it moves, connects, and remembers through these drifting pieces of frozen memory. When 3I Atlas and V1 Borisov entered our solar system, they carried no message written in words, but their very presence was a story written in ice, dust, and trajectory. Each one bore evidence of how galaxies evolve, how stars live and die, and how matter migrates across unimaginable distances. These comets were part of a lineage stretching back to the birth of their parent stars, likely formed in the cold outskirts of protoplanetary disks where sunlight was faint and molecular ices could survive. Over billions of years, gravitational encounters tore them away, ejecting them into the interstellar void. In that exile, they drifted through the galactic plane, passing through molecular clouds, magnetic fields, and cosmic radiation, their surfaces slowly etched by the passage of time. And yet, beneath their irradiated crusts, the ancient chemistry of their birthplaces remained intact, preserved like fossils of the early universe. The legacy they carry is both scientific and philosophical. From a scientific perspective, these galactic wanderers are direct samples from beyond the solar frontier. They are untouched by the heat, magnetism, and chemical alterations that have shaped local comets for billions of years. By studying them, astronomers gain a rare opportunity to examine the building materials of alien planetary systems. When telescopes captured the spectral signatures of Borisov's Comet, the cloud of gas surrounding its nucleus, they found traces of water, hydrogen, cyanide, and carbon monoxide in proportions similar to comets of our own Oort cloud. That similarity was breathtaking. It meant that the chemistry that forged life here on Earth might not be unique. Across the vast disk of the Milky Way, other suns, other worlds, may have undergone the same chemical genesis, producing the same molecular ingredients. Every comet like Borisov or Atlas becomes a link in that galactic chain, suggesting that life's potential may be woven into the very fabric of our galaxy. But beyond chemistry lies motion, the poetry of trajectory. The paths of these interstellar comets are unlike any local orbits. They arrive on hyperbolic trajectories, meaning they are not bound to our sun. Once they pass, they will never return. Their motion through our sky is brief, a few months of visibility, and then they fade into the outer dark again. This fleeting presence gives them a kind of mythic quality, like celestial nomads pausing only long enough to remind us of the greater universe beyond our reach. Astronomers can trace their past paths backward and their future paths forward, but the destinations are unknowable. They may wander for millions of more years before ever coming near another star system, if at all. That journey through endless space is part of their legacy, the endurance of matter. the persistence of existence, even when unobserved, to the human imagination. These wanderers embody both melancholy and wonder. They remind us of how small we are, and yet how connected we remain to the cosmic whole. When an interstellar comet glows in the sky, it becomes a bridge between systems, a physical thread binding distant stars. It has seen sights we cannot imagine, the birth of nebulae, the death throes of supernova, the drifting arms of spiral galaxies seen from within. It has existed longer than humanity's entire history, carrying in its frozen layers the dust of stars that perished before our planet was born. Its surface is an archive, written not in ink, but in isotope ratios and crystalline patterns, a record of interstellar weather and cosmic radiation. Studying these galactic wanderers also deepens our understanding of cosmic dynamics. The Milky Way is not a static disk. It breathes, rotates, and stirs with gravitational tides that sweep through its arms. Stars migrate, clusters disperse, and rogue planets and comets drift between systems. In this grand ballet, objects like Borisov and Atlas become the messengers of interaction. They are physical proof that the galaxy is a living ecosystem, where material is constantly exchanged between systems. They remind us that even the emptiest void is not truly empty, it's filled with motion, connection, and memory. The legacy of these wanderers extends into technology and exploration as well. Humanity's instruments, our telescopes, spectrometers, and space probes have become our senses extended into the galactic night. The detection of Borisov, for example, was made possible by the refinement of automated sky surveys and artificial intelligence algorithms that scan for movement among the stars. These technologies, developed for the purpose of planetary defense and scientific curiosity, are now uncovering cosmic visitors that rewrite our understanding of existence. And in doing so, they mirror the comets themselves, tools and travelers, carrying knowledge across generations, expanding the reach of human perception beyond what was once thought possible. There's also a more poetic legacy, a reflection on time itself. The lifespan of a comet's journey dwarfs human comprehension. While we measure our lives in decades and centuries, a comet like Borisov may have traveled for tens of millions of years before reaching our solar system. In that time, civilizations could rise and fall, stars could ignite and die, galaxies could drift and change shape. Yet, through it all, the comet continued its silent path, indifferent to time, untouched by history. Its endurance becomes a metaphor for continuity, for the persistence of matter through the shifting sands of cosmic evolution. Humanity, by observing these travelers, becomes part of that continuity, if only for a brief flicker of cosmic time. Even the names 3I Atlas, V1 Borisov reflect the union of science and human curiosity. They are catalog numbers and surnames, but also symbols of discovery. Each name marks the moment when human beings first caught a glimpse of something ancient and distant. The I in their designation stands for Interstellar, a category that barely existed before 2017, when Oumuamua was found. In just a few short years, our perspective shifted from believing that interstellar visitors were rare anomalies to realizing they may be far more common than once thought. 3I Atlas and Borisov represent a new chapter in the legacy of observation, a shift from viewing our solar system as isolated to understanding it as one stop along the galaxy's endless routes of exchange. As these galactic wanderers move beyond our reach once more, they leave behind more than data. They leave inspiration, curiosity, and a deeper sense of belonging. Through their passage, we glimpse the interconnectedness of all things, the idea that the dust beneath our feet, the water in our oceans, and the ice in their tails are made of the same cosmic ingredients. They are not alien in the sense of foreign. They are family in the sense of shared origin. They carry the legacy of matter's eternal journey, the slow recycling of atoms through stars, space, and time. They remind us that in the cosmic scale, there is no true isolation, only distance and delay. Until the next encounter, the next reflection, the next discovery that binds the universe a little closer through light and Modi on the discoveries of 3I Atlas and V1 Borisov have opened a gateway to a new era in astronomy. one in which interstellar exploration is no longer a distant dream, but a tangible frontier for human understanding. These cosmic visitors are teaching us not only about the history of other star systems, but also about the possibilities that lie ahead for studying interstellar matter directly, and perhaps, one day, for sending our own probes beyond the solar boundary. Every detection, every observation, every carefully measured spectral line is a step toward understanding how to interact with and study objects that exist outside the gravitational confines of our Sun. The future of interstellar exploration is tied intimately to these wandering emissaries, as they become the benchmarks, the trail markers, and the inspirations for missions that may one day travel to them. Currently, the primary tools for studying interstellar objects are ground-based and orbital telescopes, coupled with sophisticated computer simulations. Instruments like the Hubble Space Telescope, the James Webb Space Telescope, and large observatories on Earth allow astronomers to track their motion, measure their brightness, and analyze the composition of their comets. Spectroscopy reveals the molecular fingerprints frozen into the icy nuclei, while high-resolution imaging allows scientists to detect fragments, jets, and tail structure. Observing these details in 3I Atlas and V1 Borisov has already yielded unprecedented data, providing insights into the physics of interstellar matter and the conditions under which comets form in distant stellar nurseries. In the future, these same tools will become more refined, capable of identifying interstellar objects earlier, tracking them longer, and analyzing them with greater precision than ever before. One of the most exciting prospects for the future is the possibility of sending spacecraft to intercept interstellar comets. While the velocities of these objects relative to the Sun are enormous, often tens of kilometers per second, emerging propulsion technologies may one day allow humanity to reach them. Solar sails, nuclear-powered propulsion, and laser-driven systems could enable a probe to match trajectories with an incoming comet, carrying instruments capable of close-up analysis of its nucleus and composition. The data obtained from such missions would surpass what telescopes alone can provide, allowing direct sampling of alien material, ice, dust, and organic molecules frozen since the comet's formation. Imagine the scientific leap that could come from retrieving data from a comet that originated around a star hundreds of light-years away, effectively bringing a piece of another solar system into our laboratories. Interstellar comets also provide unique opportunities for understanding galactic chemistry. The similarity in composition between 3I Atlas and V1 Borisov suggests that these comets may not be isolated anomalies, but part of a broader class of interstellar objects carrying universal chemical patterns. Studying them over time can reveal whether there is consistency in the formation of icy bodies across different stellar systems. This, in turn, informs our understanding of the prevalence of water, organics, and other life-related molecules throughout the Milky Way. If these materials are common, then the seeds for life may be more widespread than previously imagined, drifting through space, ready to influence nascent planetary systems. The trajectory of interstellar exploration is only beginning. With each new comet, each improved telescope, and each technological breakthrough, we move closer to a future in which humanity can study these cosmic wanderers up close, learning not only about their composition, motion, and origin, but also about the interconnected story of stars, planets, and the chemistry of life across the galaxy. Conclusion of the entire script. The journey of 3I Atlas and V1 Borisov through our solar system is more than a fleeting astronomical event. It is a reminder of the universe's vastness, its interconnectedness, and the enduring stories carried by matter across light years of space and time. These interstellar visitors are not merely icy fragments. They are time capsules, cosmic messengers bearing the chemical fingerprints of distant stars and the echoes of stellar nurseries long vanished. Their nearly identical compositions, reflective behaviors, and trajectories suggest that interstellar comets may travel in families. That matter ejected from one system can drift for eons before brushing against another, and that the building blocks of planets, and possibly life, are more universal than once imagined. Through careful observation, spectroscopy, and analysis, scientists are uncovering the hidden histories encoded in their frozen cores, the ratios of water, carbon monoxide, and organic compounds, the dust and gas expelled in solar proximity, and the isotopic signatures that reveal the conditions of their formation. Each comet tells a story of cosmic survival, endurance, and the intricate physics of interstellar travel. By comparing these two extraordinary objects, astronomers are beginning to piece together a larger picture of galactic evolution, interstellar chemistry, and the potential ubiquity of the ingredients for life throughout the Milky Way. The passage of these celestial wanderers also challenges our perspective on the universe. It reminds us that the cosmos is dynamic, that stars, planets, and comets are interconnected across unimaginable distances, and that the boundaries of our solar system are merely a waypoint in the broader galactic journey. These discoveries inspire both technological ambition and philosophical reflection, encouraging humanity to consider new possibilities for exploration. From advanced telescopic surveys to future interstellar missions capable of intercepting and studying these objects directly. Ultimately, the story of 3I Atlas and V1 Borisov is one of connection, continuity, and wonder. They are mirrors reflecting the chemistry of distant worlds, carriers of molecular heritage across space and time, and symbols of the enduring curiosity that drives human exploration. By studying them, we not only learn about alien systems, but also gain a deeper understanding of our place in the galaxy, the universality of cosmic processes, and the endless possibilities that lie ahead in the exploration of the interstellar frontier.